Assalamualaikum warahmatullahi wabarakatuh. This is chapter 2 for theory machines and mechanism course. In this chapter, we're going to discuss about the velocity and acceleration analysis of mechanism. Before velocity and acceleration analysis is done, it is necessary to make position analysis. For any vector position, for example, position of point B with respect to point A could be write as RBA, which consists of distance between B and A as well as its direction. There are two ways to indicate the direction: radial and transverse vector, as shown in figure 2.1. Radial vector indicate by IR, while transverse vector indicate by I theta. Velocity is basically differentiation of position vector. When you differentiate position vector, you can get R dot in IR direction and R theta dot in I theta direction, as shown here. This is the formula for velocity. You no need to memorize this formula because it will be given in the exam. If the distance between A and B is constant, the value of R dot is 0. Then you can simplify the formula to R theta dot only. Let's see an example here. This mechanism has 4 links. Velocity analysis of mechanism should be start at input link, which in this case is link number 2. Velocity at point B with respect to point O2 is given by this formula because distance between B and O2 is fixed and value of R dot is 0. You can write VBO2 as VB because the point O2 is at the ground and you can omit that. Next, you can find the velocity of point C with respect to point B, which is given by this formula. If you want to find the velocity of point C with respect to ground, then you need to add VCB and VB. This velocity also known as absolute velocity of point C. Point B, C and D are located at link 3. Therefore, theta dot CB is equal to theta dot CD is equal to theta dot BD and is equal to theta dot 3. You need to remember that theta dot is an angular velocity, which is different from linear velocity. This example is a slider on a straight slide. There are 3 links here: ground, straight slide, and slider. For simplicity, point B is divided into B2 and B3, where it is at a link 2 and 3 respectively. Distance between point B2 and point A is fixed, while distance between point B3 and B2 is 0. Therefore, R dot B2A is 0, but R dot B3B2 is not 0. R dot B3B2 is not 0 because point B2 is on the link 2 while point B3 is on the link 3. When the slider moves, there is velocity difference between B3 and B2. The first thing that you need to do is to calculate the velocity at point B2 with respect to point A or ground. Therefore, you can write as VB2 is equal to RB2A theta dot B2A in I theta direction. Of course, theta 2 dot B2A is equal to theta 2 dot because both point B2 and A is at link 2. Next, you need to find the velocity at point B3 with respect to point B2, which is equal to R dot B3 B2 in IR direction. We can eliminate this term here because RB3 B2 is 0. That is the reason why we split the point B into B3 and B2. Therefore, absolute velocity of point B3 is summation of VB2 and VB3B2. Next, we are going to discuss about acceleration analysis. Acceleration basically is differentiation of velocity. Therefore, we just differentiate velocity formula, which is give this formula. This formula also will be given in your exam. There are 4 parts of acceleration, which are sliding acceleration that give you formula of R double dot, normal acceleration that give you formula of negative R theta dot, tangential acceleration that give you formula of R theta double dot, and Coriolis acceleration that give you formula of 2 R dot theta dot. Both sliding and normal acceleration are in IR direction, while tangential and Coriolis acceleration are in I theta direction. This slide explains to you about normal acceleration and the reason for it to be a negative sign. This slide is explained about the sign convention used for acceleration analysis. Positive sign is when rotation is anti-clockwise and move away from the point of reference. Therefore, sign for Coriolis acceleration is depend on the direction of theta dot and r dot. If theta dot is anticlockwise and r dot is away from the point of reference, Coriolis acceleration is positive. If both theta dot is clockwise and r dot is moving towards point of reference, Coriolis acceleration is positive. This slide shows summary of Coriolis acceleration sign convention. This slide shows summary for all components of acceleration analysis with its direction. You can pause this video to really digest their directions. If distance between point A and point B is fixed, r dot is equal to 0 and r double dot is equal to 0. Therefore, both sliding and Coriolis acceleration is equal to 0. Now, let's look at an example similar to velocity analysis example. Acceleration at point B with respect to the ground is given by the normal acceleration of negative r theta dot square and tangential acceleration of r theta double dot because distance of point B and ground is fixed. Furthermore, if angular acceleration of link 2 theta 2 dot is constant, that means theta 2 double dot is equal to 0 because differentiation of a constant gives you 0. Then, you only left with normal acceleration because tangential acceleration is equal to 0. Acceleration of point C with respect to the point B is given by formula of negative r theta dot square and r theta double dot because distance between point A and point B is fixed. If you want to calculate absolute acceleration of point C, you need to add acceleration of point C with respect to point B and acceleration of point B with respect to slider on a straight slide. R B2 B3 is equal to 0. Then normal and tangential acceleration are equal to 0. Therefore, its acceleration component only sliding and Coriolis acceleration. For slider on a curved slide, there is a new component added, which is a normal acceleration. However, this normal acceleration formula is different from previous one because this normal acceleration is due to the curved slide, which is equal to the radius of the curve times theta dot square in direction toward the center of the curve, which gives you negative sign. Next, we are going to discuss about limit positions. Limit positions are the maximum and minimum points of a link it can travel in a mechanism. For example, this slider in a slider crank mechanism has D1 and D2 as 8 limit positions. Distance between limit position is a stroke. This slide shows how to calculate stroke length for an offset slider crank mechanism. Please note that the angular distance delta theta 2, which represent angle required for the crank to travel to move slider from one limit position to another. This distance is not the same when slider travel in opposite direction. Therefore, time taken to the left and to the right is different as shown here. Time ratio, on the other hand, ratio time taken to move to the left and to the right. It could be concluded that average velocity of the slider to the left and to the right is different as shown here. This slide shows example with value for calculation average velocity to the left and to the right. Similar concept could be used for crank rocker mechanism. However, instead of a stroke in a linear distance, it replaced with angular distance of delta theta 4. Calculation for average velocity counterclockwise and clockwise similar to the previous example. This slide shows example of a quick return mechanism. You can observe the same concept have been used here as well to calculate time ratio. Transmission angle is another consideration when you design a 4-bar mechanism. Optimum transmission angle is 90 degrees because all the forces in the link could be used to move another link. However, this optimal angle cannot be maintained in a moving mechanism. Therefore, acceptable transmission angle is between 45 degrees to 135 degrees in a 4-bar linkages. Minimum transmission angle between link 3 and 4 here is when theta 2 equal to 0 degree and maximum when theta 2 equal to 180 degrees as shown in the figure B and C. For a slider crank mechanism, minimum transmission angle between link 3 and 4 is when theta 2 equal to 90 degree and maximum when theta 2 equal to 270 degree. This slide shows the effect of a small transmission angle. It could be observed that the most of the forces in the link 3 is almost parallel to the link 4, which is not contribute toward moving link 4. This slide shows how to sketch a graph of the transmission angle phi versus input angle theta 2. There may be a question asked to sketch transmission angle in exam. What you need to do is to calculate the maximum and minimum transmission angle, then you can sketch those values in a graph because you know that minimum angle is at theta 2 equal to 0 and maximum when it equal to 180 degree if it is a 4-bar linkages mechanism. Instantaneous center of velocity is another term that you're going to use for velocity analysis. When link is moved, it will create an instantaneous center of velocity. For example, 2 points on a rigid body A and B have a velocity of VA and VB respectively will create an instantaneous center at a point P12. The instantaneous center could exist outside the rigid body. The instantaneous center could be determined by taking perpendicular line from velocity direction. Then, the intersection of the line is the instantaneous center. If the velocities are parallel, its magnitude will determine location of the instantaneous center. If the magnitudes are the same, then the instantaneous center is at infinity. However, if they are parallel but opposite direction, then the instantaneous center is at the middle. This slide shows a typical kinematic pair and location of its instantaneous center. The link pair gives instantaneous center at the joint, sliding pair on the curved slide at the center of the curve, and sliding pair on the straight slide give you an instantaneous center at infinity. For a rolling pair, the instantaneous center is at the contact point and rolling in a straight slide is at the center of the rolling body. For a mechanism, number of instantaneous center depend on number of links using this formula, where P is number of instantaneous center in that mechanism and N is number of link. For example, 4-bar linkages will have 6 instantaneous center, where this figure shows 4 of them, which are P12 between link 1 and 2, P23 between link 2 and 3, P34 between link 3 and 4, and P14 between link 1 and 4. Kennedy's theorem is used to determine another 2 instantaneous center points. Before you use Kennedy's theorem, you need to make sure that the mechanism drawing is accurate to its dimension and position. Otherwise, you will get a wrong answer. In the exam, you need to draw accurately using a proper scale for the mechanism. For a 4-bar mechanism, you need to draw a square and write the link number at each corner of the square. Then, you need to create triangle within the square. Triangle will indicate points on the mechanism. The first triangle here connecting 1, 2 and 4 that will give you point of P12, P14 and P24. Therefore, you need to create a line in the mechanism that connect these 3 points. You have point 1, 2 and 1, 4 here, but still do not have point 2, 4. Therefore, you need to extend the line beyond P12 and P14. You repeat the process for the second triangle here, where you draw a line connecting P23, P34 and P24. The intersection between the line is a point P24. Now you got 5 instantaneous center points. You need to find one more point, which is P13 using second square with the same process. Next, you look at the slide diagram mechanism, which has 4 links and 6 instantaneous center points. The first 3 points on the mechanism are P12 between link 1 and 2, P23 between link 2 and 3, P34 between link 3 and 4. There is another point which is P14 between link 1 and 4, but since link 4 is sliding on the link 3, the instantaneous center point is at infinity. To find another 2 instantaneous center point, Kennedy's theorem is used. Point P13 found by having line connecting P12 and P23 as well as line connecting P14 and P34. Point P24 found using line connecting P23 and P P34 as well as the line P12 and P14. You have to remember that the line P14 is at infinity. You can try this another example of 4-bar mechanism. Please make sure that you try before you see the answer. This slide shows an example of 3 links that have 3 instantaneous center. The third instantaneous center point is between line P12 and P13 as well as the common normal. This slide shows a 6-link mechanism that has 15 instantaneous center points. 8 of them are the obvious one, while another 7 you need to use Kennedy's theorem. Why instantaneous center is important? We can use instantaneous center to do velocity analysis. You need to use this formula to do velocity analysis using instantaneous center. Let's see an example. In this example, you need to find the velocity of link 4 or point D. There are 2 methods to do this. The first method using value theta2 dot to calculate value theta3 dot. Then using the value of theta3 dot to calculate velocity of point D. Second method using value of theta2 dot to calculate value of theta4 dot. Then velocity of point D is calculated. This is another example that use instantaneous center to determine velocity of point B. Another example is the 3-link mechanism where you can determine theta3 dot value using theta2 dot value. This method is the basis for calculation of gear mechanism. Lastly, you can try yourself this example to practice your knowledge in using instantaneous center to perform velocity analysis. That is all from me for chapter 2. If you have any question, you can ask me in the comment below.